Hello, geometry students. Welcome to our 13.1 to 13.2 notes. This is the beginning of our last unit of the year. We're going to be studying probability, and in the study of probability, it's very important to learn how to count things. And sometimes counting is a matter of just being really organized. So let's take a look at this first example, and let's imagine this scenario where we toss a coin and then we roll a number cube. Now that number cube would have the numbers 1 through 6 on it, or it might have dots like the cubes you play board games with. So let's represent the sample space. That would be all the possible outcomes of this experiment in 3 ways. We're going to make a list, we're going to make a table, and we're going to make it what's called a tree diagram. So let's start with our list, and to be organized, let's think of all the ways that we could toss the coin and get a heads. So we could get a heads and then roll a 1, get heads on the coin, roll a 2, get heads on the coin, roll a 3. We could get heads with a 4, heads with a 5, or heads with a 6. So that's all the ways, all the outcomes that would happen if when we toss that coin we get a head. But of course there's another outcome, and that is you can toss a coin and get tails. So let's list all those possibilities. So we could roll a tail, or flip a coin, get tails, and then roll a 1. We could do tails and then roll a 2. We could get tails and a 3. We could flip a coin, get tails, and then roll a 4, and then tails and 5, tails and 6. So we can see that that's an organized way to list all the possible outcomes. Another way to do that is to use a table, and this is going to look very similar actually to the list. Let's just make a table that has 2 rows and it has 6 columns. Okay, and so we can either get heads or tails when we roll that coin, and then when we roll the number cube, we could get a 1, 2, 3, 4, 5, or 6. Okay, so all those possible outcomes, we could just use the table. Heads 1, heads 2, heads 3, and so on. 5, heads 6, and then tails 1, tails 2, tails 3, and so on. All right, so that's the way we can just represent our sample space in an organized way using a table. Another is to use a tree diagram. It's called a tree diagram because it sort of looks like a tree, and maybe a branch rather. So we talk about our first possible outcome would be what we get when we roll that or flip that coin. We could either get heads or we could get tails. Now, after we've flip the coin, then we'll roll the number cube, and then there's 6 possible outcomes for that. So out of this branch, we need to have 1, 2, 3, 4, 5, 6 outcomes, and the same thing with the tails. There needs to be 6 outcomes. And so we could either roll a 1, a 2, a 3, a 4, a 5, or a 6, and the same thing after we roll flip the coin and get tails, we could roll the dice and get any of the numbers 1 through 6, okay? So you can see if you follow along the branches of this tree, we can find all the possible outcomes, heads 1, heads 2, heads 3, and so on. All right, let's take a look at another example. This one says make a tree diagram for the sample space of sandwich choices. So when you choose your sandwich, you can choose a bread. We can have white wheat or rye. Meat, we can have turkey or ham, and then we can have either Swiss cheese or cheddar cheese. So let's start by listing all the possible outcomes for your bread choice first. So we could either choose white or wheat, or we could choose rye bread. Okay, after that choice, then we need to make a meat choice. Now there's 2 possible outcomes for meat choice. We could either choose turkey or ham. So since there are 2 possible outcomes, I'm going to draw 2 branches coming out of each bread choice. Okay, and at each end of that we'll put either turkey or ham. Turkey or ham, turkey or ham. Then after we've made a bread choice and a meat choice, then we have 2 cheese choices. So out of each of those meat choices, I'm going to draw 2 branches. Okay, and after we've made our bread and meat choice, we can choose either Swiss or cheddar, Swiss or cheddar, all the way down. Or cheddar, Swiss, or cheddar. Okay, so now what we're going to do is we're going to just follow the tree branches and write each possibility, and that's called our sample space. So let's start with choosing white bread. We could choose white bread and then turkey and then Swiss cheese, or we could choose white bread and then turkey and then cheddar cheese. So that would be, okay, I just followed this branch, white, turkey, and cheddar. Let's stick with wet bread, or white bread. Yuck, not wet bread, white bread, and let's choose ham. So if we choose white bread and then ham, we could either choose Swiss or white bread, ham, and cheddar, okay? Those are all the possible sandwiches using white bread, so now let's move on to the wheat bread. So wheat bread, first meat choice is turkey, first cheese choice is Swiss, so we'll say wheat, turkey, Swiss, or we can have wheat, turkey, and cheddar. What about if we chose wheat bread but then chose ham? So we can have wheat, ham, and Swiss, or wheat, ham, and cheddar, okay? And those are all the sandwiches we could make if we chose wheat bread. Now let's move on to rye bread. So we could start with rye bread. We could choose turkey and then cheddar. So rye, turkey, cheddar, or we could choose rye, turkey, and Swiss. Or we might, rather instead of having turkey, we might choose ham after we make the choice of rye bread. So that would be rye, ham, and Swiss, or rye, ham, and cheddar. So you can see that there are a total of 12 possible outcomes. Okay, so we're thinking about ways that we could list possible outcomes in an experiment. Now let's talk about how we can count them. So let's learn what's called the fundamental counting principle, which says the number of possible outcomes in a sample space can be found by multiplying the number of possible outcomes from each stage or event. So if we go back to that last example, there were three bread choices, okay, 2 meat choices and 2 cheese choices. So if we take 3 times 2 times 2, that's going to be 12, and if you count here, you'll see that there are 12 possible outcomes. Let's look at a couple other examples. How about example 3 that says, find the number of possible outcomes for each of the following, the number of possible answers on this answer sheet. So you'll see that there are 10 questions. Question number 1, there are 4 possible choices. So I'm going to write down a 4. And then question number 2, there are 4 possible chances. And the same thing for numbers 3, 4, 5, and 6. So I'm going to multiply 4 by itself a total of 6 times. Let me count, make sure I did that right. So 1, this is question 1, question 2, question 3, question 4, question 5, question 6. Then we can see that questions 7, 8, 9, and 10 are true or false. So that's 2 outcomes. So 2 possibilities for question number 7, 2 for 8, 2 for 9, 2 for 10. So you can tell before we actually multiply this is going to be a very gargantuan number. All right, so the probability of guessing right on a question, on a test like this, would be very, very unlikely, because if you multiply all this out, there are 65,536 possible outcomes. So your probability of guessing right on every single one of them would be 1 out of 65,536. Not very good odds. How about this? If a die or a number cube is rolled 4 times, well, every time we roll the number cube, there are 6 possible outcomes. So there's 6 possible outcomes on the first roll, and 6 possible on the second, and the third, and the fourth. So if we multiply 6 by itself 4 times, we get a total of 1,296 possible outcomes. And then one more example, a pair of shoes comes in whole sizes, so we can talk about shoe size. Then we can talk about color, red, navy, brown, or black. Then we can talk about the material used, either leather or suede, and then there are 3 widths available. So how many possible shoe combinations are there? Well, we'll take the number of shoe sizes. Now, if you count all the sizes from 5 to 11, that would be a total of 7 sizes. 5, 6, 7, 8, 9, 10, 11. That's 7 sizes. There are how many colors? 1, 2, 3, 4 colors. So we'll multiply that by 4. There are 2 material choices, leather or suede. So we'll multiply that by 2. And then there are 3 widths. So we'll multiply that by 3. So the total number of possible outcomes of shoes would be 168. Okay, so now let's get into some probabilities using what are called permutations. So permutations are outcomes. A permutation is an arrangement of an object or an outcome where order matters. This is really important that you recognize that if order matters, that's when you're talking about a permutation. So let's look at some examples to learn about this. Example A, how many ways can Mark, Nikki, Jose, and Jacqueline line up in line for concert tickets? Well, think of, okay, that line, there are 4 spaces in that line. So let's just put 4 blanks for right now, okay? And let's say we randomly chose one of these 4 friends to stand in the first spot. Well, there are 4 choices there, so I'm going to put a 4 here. Now, after I've made that first choice, now there are only 3 people left for this spot. So we're going to take 4 and multiply it by 3. And then in this third spot, now there are only 2 people left. And then finally, when you go to make that last choice, there's only 1 person left. So 4 times 3 times 2 times 1 turns out to be 24. That's called 24 ways, or we can say there are 24 ways of that happening. Now, this is going to happen a lot where we take a number and we multiply it by every integer smaller than that number all the way down to 1. There's a symbol for that, and it's an exclamation point. It looks like this. 4, and it's not like you're emphasizing 4, that's just what this means is, it's called 4 factorial, and it means 4 times 3 times 2 times 1. So I just wanted you to see this symbol because we're going to be using it a lot today. Example number 2 says, what is the probability that Mark lines up first and Jose lines up last? So if we write down those 4 spots again, okay, if we put Mark in the first position and Jose in the last position, that means we only have 2 people left to fill this spot, and once we have filled that spot, then we only have 1 person left for the last spot. So how many ways can this happen? There are 2 times 1, or we actually could say 2 factorial ways of this happening. But notice we weren't asked just how many ways how many ways can this happen. We're asked what is the probability. So to find a probability, that answer is going to be a ratio. So the probability would be the number of ways that it can happen, which is 2 factorial, over the total possible outcomes. Well, we found that out in point A, or part A, there were 24 possible outcomes. So we get 2 factorial over 24. That's 2 times 1 over 24, or that would just be 2 over 24, or we could reduce that to 1/12. Okay, let's take a look at another example. Pete and Alex are members of a basketball team where every player is randomly assigned a jersey numbered from 1 to 20. What is the probability that Pete's jersey will be 1 and Alex's jersey will be 2? Well, let's count how many ways that can happen. So imagine that there are 20 jerseys, so there are 20 spots, so we can say one. I'm just going to kind of start this process, but of course we can't, or we could, but we're not going to take the time to list all of that, so I'm just going to put a ... Okay, so the probability of Pete, this P parentheses is a way of saying probability of, the probability of Pete randomly getting jersey number 1, so Pete number 1, and Alex getting randomly getting jersey number 2. Well, let's count all the ways that could happen. Well, if Pete has number 1 jersey, oh, that's supposed to be a, let me erase that. If Pete has jersey number 1 and Alex has jersey number 2, so let's say that happened randomly, then how many jerseys are left for this person? Well, now there's 18 left, okay? And then after that person's been assigned a jersey, then there's 17 for the next, and so on down the line. Okay, so what is the probability of Pete randomly getting jersey number 1 and Alex randomly getting jersey number 2? Well, there are, as you can see, there are 18 times 17 times 16 times 15, etc. That's called 18 factorial ways of that happening. So 18 factorial out of, there are 20 factorial possible outcomes. Because remember, there are 20 jerseys for the first person, and then 19 for the second, and 18 for the third, and so on. So 18 factorial over 20 factorial. So let's talk about how we could simplify that. Well, I'm just going to write 18 factorial in the numerator and then start writing 20 factorial in the denominator. So that would be 20 times 19, and then times 18 times 17 times 16, etc. In other words, times 18 factorial. So I wrote it that way so that I can actually cancel this 18 factorial. So that means all we have to do is multiply 20 times 19 to get our final answer, and our final answer is the probability of Pete randomly getting jersey number 1 and Alex randomly getting jersey number 2 would be 1 over 20 times 19, or 1 out of 380. Okay, so now it's time to learn a formula for the number of permutations of n distinct, that means different from one another, n distinct objects taken r at a time. And there's a symbol we use for that. It's a capital P for permutation, and then we have a kind of a subscript in front of the P for n. N is the number of objects, and then we put a subscript of r to the right of the capital P, and that would be how many times they're taken. So in other words, when you see this symbol, what that means, it's the permutation of n things taken r at a time. Now, there's a formula for calculating that, and it looks like this. It's going to be n factorial over n minus r factorial. All right, so let's look at some examples where we actually use that formula. So example 6 says, how many ways could a dance coach randomly choose a captain and a squad leader to perform a duet from a group of 5? So, and this is a situation where she's not just choosing 2 people, she's choosing 2 people and assigning them a position. One's a captain, one's a squad leader. So that means order matters. If order matters, if she's just randomly picking 2 people, order doesn't matter. Here, order matters because the first person is going to be a captain, the second person is going to be a squad leader. So if order matters, we know we're doing a permutation. So what we're doing a permutation then to count the number of possible outcomes, it's a permutation of 5 people. Remember, there are 5 in the group, taken 2 at a time. So the formula would tell us to take 5 factorial over 5 minus 2 factorial. So let's simplify that. That would be 5 factorial over 3 factorial. And then we can reduce this fraction quite a bit. Let's go ahead and write 5 factorial as 5 times 4 times 3 times 2 times 1, which would be 3 factorial, all over 3 factorial. Now we did that so that we could cancel the 3 factorial, and we see that there are 20 ways that there are 20 ways that could happen, that she could choose 2 people, one to be a captain, one to be a squad leader from a group of 5. Okay, so the question was, how many ways can that happen? So we've answered the question. There are 20 ways. Notice this was not a probability question. It was just asking how many ways that could happen. Okay, example 7 says, how many ways could a photographer randomly choose 4 friends? Notice it says in order, okay, from a group of 6 for a picture. So since order matters, like you're going to say, Sally, you're going to be in the first position, and John, you're going to be in the second position, etc. So since order matters, this is a permutation. So we're going to say we're going to take a permutation of 6 people taken 4 at a time. Okay, so if we use this formula up here, this is n, so we're going to put 6 factorial in the numerator over 6 minus 4 factorial, and then we can simplify that. So it would be 6 factorial over 2 factorial, or this would be 6 times 5 times 4 times 3 times 2 factorial over 2 factorial. So we wrote it out like that so we could cancel the 2 factorials. And then we'll take 6 times 5 times 4 times 3, and we will get 360. So we were asked, how many ways can that happen? There are 360 ways that a photographer could choose 4 friends from among 6 in order. Okay, the next example, Mickey Mouse, Donald Duck, and Goofy join a club with 15 members. So they are 3 of the 15 members, okay? So the 15 includes these 3. If leaders are chosen randomly, what is the probability that Mickey, Donald, and Goofy are chosen to be president, vice president, and secretary respectively? Now what this respectively means is we have 2 lists. We have Mickey, Donald, and Goofy, and then we have president, vice president, and secretary. So respectively means that the first person in this, the first item in this list is paired with the first item in this list. The second item in the second list is paired with the second item, and so on. Okay, so this is a permutation because we're not just saying what is the probability that a person would pick Mickey, Donald, and Goofy randomly from a group of 15. We are assigning them position. Order matters. What is the probability that Mickey is the president, Donald Duck is the vice president, and Goofy is the secretary, respectively? So since order matters, this is a permutation. It's a permutation of 15 people taken 3 at a time. So according to our formula, that's going to be 15 factorial over 15 minus 3 factorial. So that would be 15 factorial over 12 factorial. Now let's reduce. So this is 15 times 14 times 13 times 12 factorial over 12 factorial. The 12 factorials cancel. So we get 15 times 14 times 13, which is equal to 2,730. Now notice what the question says. The question says if the leaders are chosen randomly, what is the probability? So this isn't just asking us how many ways that can happen. It's asking what is the probability. Well, there's only one way that could happen, and so our final answer is going to be 1 out of 2,730. That's the probability. Okay, how about this example? It says a student identification card consists of 4 non-repeating digits. What is the probability that a randomly generated card has the ID number 4231? Now this is a situation where order matters because 4 has to occupy the first position, 2 has to occupy the second position, and so on. So since order matters, this is a permutation, and it's going to be a permutation of 10 digits. Now, the reason why there are 10 digits is because we have to count 0. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a total of 10 digits, and we're taking them 4 at a time. So the permutation of 10 items being taken 4 at a time is equal to 10 factorial over 10 minus 4 factorial, or that would be 10 factorial over 6 factorial. Now let's reduce 10 times 9 times 8 times 7 times 6 factorial over 6 factorial. And if we multiply 10 times 9 times 8 times 7, we get 5,040. So what is the probability then? There's one way we can have 4 and then 2 and then 1 and 3. So there's one way out of 5,040. So our final answer would be 1 over 5,040. Okay, so next we're going to take a look at this formula. It's permutations with repetition. So the number of distinguishable, so that's one difference from another, distinguishable permutations of n objects in which one object is repeated are 1 times, another is repeated are 2 times, and so on, is the following. That formula is going to be n factorial, now that's the number of items you have, divided by r sub 1 factorial times r sub 2 factorial times r sub 3 factorial, just keep going until times r sub k factorial. Now, one thing to notice is that this r represents the number of times that something repeats. So keep in mind that r represents the number of times that something repeats. So let's use this formula in this next example, which says, what is the probability of randomly selecting a permutation of these letters that actually spells Mississippi? Okay, so order matters, obviously. If order matters, or it wouldn't spell a word. So this is a situation where we have repeating elements. If you count, you can see that let's see, the letter I occurs 4 times, the letter P occurs 2 times, and the letter S occurs 4 times. All right, so following this formula, n, remember, is our number of letters. So if you count 1, 2, 3, 4, 5, 6, 7, you count up, there's 11 possible, or there are 11 numbers here. So that means to find the number of permutations, we're going to take 11 factorial, and we're going to divide it by, now, I occurs 4 times. I occurs 4 times. So remember, the number of distinguishable permutations of n objects in which one object is repeated are 1 times. So we're going to put in the denominator, we're going to put a 4 here. Then we're going to multiply that by 2 because the letter P occurs 2 times, or excuse me, 4 factorial and 2 factorial, and then times another 4 factorial because we have another letter S, that's a fraction bar, we have another letter S that occurs 4 factorial times. So this might be a good time to use a calculator. There is a factorial button on the calculator, and so when we do that, we get that 11 factorial is equal to 39,916,800, okay, out of, when we take, let's see, 4 factorial times 2 factorial times 4 factorial, that turns out to be 1,152, and then if we do that division, we get 34,650 ways that we can choose these numbers. So what is the probability of selecting these letters randomly and actually spelling a word? That can only happen one way, so our probability would be 1 out of 34,650. Then let's do another permutation with repetition. Example 11 says, what is the probability that a 7-digit telephone number with these digits, these digits actually turns out to be the number 5565211? Okay, so the first thing we're going to do is see how many numbers we're choosing from. There are 1, 2, 3, 4, 5, 6, 7 total numbers in this list. So that means we're going to take 7 factorial and put that in the numerator. And then in the denominator, we're going to find out what repeats. Well, I see that 5 repeats 1, 2, 3 times. So 5 repeats 3 times, okay? And also I see that the number 1 repeats twice. So the number 1 repeats 2 times, okay? So according to the formula then, to find the number of ways that, another number of outcomes that could happen, we would put 3 factorial in the denominator times 2 factorial. Again, we're not putting the number 5 or the number 1 in the denominator. What we're putting is the number of times that those numbers occur in this list. So 7 factorial over 3 factorial times 2 factorial. I think this one we can do by hand. So I'm gonna do the following. I'm just gonna write 7 factorial as 7 times 6 times 5 times 4 times 3 factorial, and put that over 3 factorial times 2 factorial. The reason I wrote it like that is so that I can cancel the 3 factorial. And so the numerator, 7 times 6 times 5 times 4, is 840. And the denominator, which is 2 times 1, is just 2. So this turns out to, 840 divided by 2. So turns out to be 420 ways that can happen. So what is the probability, or 420 outcomes, but there's only one way we can get this number. And so the probability then is going to be, I'll write it over here, 1 over 420. Okay, the next thing we're going to talk about then is a circular permutation. A circular permutation is the number of distinguishable permutations of n objects arranged in a circle with no fixed reference point. So we'll talk about that fixed reference point more in a minute, but here's an example of some spices that are arranged in a circle. So to find the number of distinguishable permutations, we'll use this formula. If we have some time in class, maybe I'll derive this for you, but I'm trying to keep this video a little bit shorter. So it's n factorial over n, or another way to write that same formula would be n minus 1 factorial. They're the same thing. If you take, well, I can just show you. If we take this, if n factorial would be n times n minus 1 factorial all over n. Those n's would cancel. So you can see that n factorial over n is the same thing as n minus 1 factorial. So for example, let's take a look at this example. What is the probability that 6 charms chosen randomly would produce the arrangement shown? Well, since this is a circular permutation, we'll use this formula, n factorial over n. So how many objects are there? There are 1, 2, 3, 4, 5, 6, 7. Oh, I don't think this isn't an object. This is just a little, like, I don't know, the little tag on it. These are the actual charms. So 1, 2, 3, 4, 5, 6 charms. So to find how many ways, or what the probability of them being arranged in this order, we need to find the possible ways that that can happen. So that since there are 6 charms, it would be 6 factorial over 6, which is 6 times 5 factorial over 6. Those 6's cancel. We just get 5 factorial, which is 5 times 4 times 3 times 2 times 1, which is 120. So the probability of this happening would be 1 over 120. Now I just want to show you the other way. We could have also just taken n minus 1, 6 minus 1 factorial, and we would have ended up with 5 factorial and gotten the same outcome. So the probability of this arrangement happening is 1 out of 20. Okay, in this next example, it says you are seating a party of 4 people at a round table. One of the chairs is next to a window. If the diners are seated at random, what is the probability that the person paying is seated next to the window? So that's what we call like a reference point. So let's just maybe draw a picture. So we've got our round table. We're going to seat 4 people around that table. And let's just draw a little rectangle here. That represents the window, okay? So what is the probability that the person paying sits next to the window? Well, we've been talking about circular permutations, but as soon as we have a fixed reference point, it's really not a circular permutation anymore. Now it's just a linear permutation. So it's like, what's the probability that this guy's in the first spot and then these guys line up behind him? So that probability would be, well, let's talk about the number of ways that could happen. There are 4 factorial outcomes here because we could put anybody in this first spot, in this spot next to the window. So there's 4 here possibilities. Then once that person is seated, then there'd be 3 for this seat, 2 for this seat, and 1 for this seat. So there are 4 factorial possible outcomes. But what is the probability that the payer is sitting next to the window? So think of those 4 spots, okay? Let's say the payer is in that spot next to the window. That leaves 3 people for the next spot, 2 people for the next spot, and then 1 person for the next spot. So in other words, the probability is 3 factorial over 4 factorial. Well, 3 times 2 times 1 is 6, and 4 times 3 times 2 times 1 is 24. So that turns out to be 6 out of 24, or there's a 1 out of 4 chance that the payer sits next to the window. Okay, example 14 says, a football team's 11 players get in a huddle before a play. What is the probability that the fullback stands to the right of the quarterback if the team huddles together at random? Now, there's no fixed reference point here, so we're going to use circular probability. So I'm actually going to kind of draw a picture of what's happening here. So let's say we have the quarterback gets in the circle, and then the fullback stands next to him. Now, there are 9 more players left. So in this next spot, there's 9 people. There's 9 left, and then 8, and then 7, and then 6, and then 5, and then 4, and 3, and 2, and 1. So that's all the possibilities that, all the ways that the fullback could stand next to the quarterback. Now, to make this a probability, though, we have to put that over. So I'm going to make this kind of look like a ratio. That needs to be over all the possible ways of lining up. So we're going to put the quarterback in the first spot, okay? So if the fullback could be anywhere, that means that there are now 10 people that could stand next to the quarterback, and then 9 in the next spot, and then 8, and then 7, and then 6, and 5, and 4, and 3, and 2, 1. So that's kind of a picture of the math we're going to write. So that means there are 9 factorial ways that the fullback could be standing next to the quarterback out of 10 factorial ways of lining up with the quarterback in the circle. So 9 factorial over 10 factorial would be 9 over 10 times 9 factorial. So we can cancel the 9 factorial, and we get 1 out of 10. So if there's no fixed reference point, the probability that if they get in a huddle and the fullback stands next to the quarterback, that can happen 1 out of 10 ways. Now, part B says, If the referee stands directly behind the huddle, what is the probability that the referee stands behind the halfback? Okay, so now the referee creates what we call a reference point. So this really isn't a circular permutation anymore. Now it's just a linear permutation. So I'm just going to put an R for the to represent the referee, which is our fixed reference point. And then I'm going to stand him next to the halfback. Okay, now once the halfback is in position, that means that there are 10 guys for the next position, and then 9 for the next, and 8, and so on. Okay, so that's all the ways that we can line up with the halfback, or the referee standing next to the halfback. Now, we need to make this a probability, so out of the total ways that the team can line up, well, there's 11 guys for this first spot, and then 10 guys, and then 9, etc. Okay, in other words, this is going to be 10 factorial over 11 factorial, or 10 factorial over 11 times 10 factorial. I wrote it like that so I can cancel the 10 factorial, and we see that the probability is 1 out of 11. Okay, so now we're going to switch gears and talk about probabilities using combinations. So a combination is an arrangement of objects where order does not matter. Okay, so permutation, order did matter, but for combinations, order does not matter. So let's learn a new formula. The number of combinations of n objects taken r at a time looks like this. Now we're going to use a capital C for combination, but then we still use n for the number of objects and r for the how many objects are taken at a time. That formula is the following: n factorial over n minus r factorial times r factorial. All right, so let's take a look at some examples. Example 15 says, how many ways can you choose 3 t-shirts from among 8 t-shirts in your drawer? Now, here's a situation where order doesn't matter. It's not like I'm choosing a t-shirt to wear on Monday, and a different t-shirt to wear on Tuesday, and a different t-shirt to wear on Wednesday. Order does not matter. Just any group of 3 from among the 8. So since order doesn't matter, that's a combination. So it's going to be a combination of 8 things taken 3 at a time. So using our formula, that means we're going to have 8 factorial in the numerator, and then 8 minus 3 factorial times 3 factorial. Okay, remember in this situation, n is 8 and r is 3. Okay, so let's simplify that a little bit. That would be the same thing as 8 factorial over 5 factorial times 3 factorial, because 8 minus 3 is 5. And then if I break this down a little bit, we'd have 8 times 7 times 6 times 5 factorial. I wrote it like that because I have a 5 factorial in the denominator, and I want to be able to cancel those. So that turns out to be, now hold on, before I multiply, I was about to start multiplying, but then I realized that 3 factorial is 3 times 2 times 1, which is 6. So that means I can cancel this 6 with this 3 factorial, and I'm left with just 8 times 7 in the numerator. So how many ways then are there of choosing 3 t-shirts from among the 8 in your drawer when order doesn't matter? There are 56 ways that can happen. Okay, how about this next example that says there are 20 different colored crayons in a box. What is the probability of randomly choosing each of these colors? Red, yellow, green, blue, purple, and orange. Okay, so how many, let's count. How many colors are we talking? 1, 2, 3, 4, 5, 6. So how many ways are there? If order doesn't matter, it's not like I'm going to choose the red one first and the yellow one second. I'm just choosing those colors from among 20. So that's a combination. So that would be a combination of 20 crayons taken 6 at a time. So using our formula, that would be 20 factorial over 20 minus 6 factorial times 6 factorial. Or if I simplify a little bit, that would be 20 factorial over 14 factorial times 6 factorial. Or that would be, let's see, 20 times 19 times 18, times 17 times 16 times 15 times 14 factorial. all over 14 factorial times, now I'm going to write this 6 factorial. I'm going to go ahead and write it out. And you'll see why I'm going to do that in just a second. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, because I'm looking for stuff I can cancel. For example, I can cancel, let me get some colors here. I can cancel 14 factorial with 14 factorial. Also, I'm looking for other factors that can cancel. For example, I could cancel 5 times 4 is 20, so I can cancel that with 20. I can cancel 6 times 3 is 18, so I can cancel with 18. And then there's also this factor of 2 in the denominator, so I'm going to look for something even up here like 16. So 2 goes into 2 once, and 2 goes into 16 8 times. So that means, look at the denominator. Everything has been canceled except for 1. And then what we have left in the numerator, I have 19 times 17 times 8 times 15. If you multiply that all together, let's see, we get 38,760. So this is equal to 38,760. So what that means is the probability of randomly drawing these 6 colors from among the 20 in the box, the probability would be 1 out of 38,760. All right, and then our last example says if 3 points are randomly chosen from those named on the rectangle shown, what is the probability that they all lay on the same side of the rectangle? Okay, so what we're asking then, if we count, there are a total of 1, 2, 3, 4, 5, 6, 7, 8 points. And then if you notice, each side has 3 points. So order doesn't matter, so we're looking at a combination of 8 points chosen 3 at a time. So that amount would be 8 factorial over 8 minus 3 factorial times 3 factorial, which is 8 factorial over 5 factorial times 3 factorial. All right, and then we can simplify that. That would be 8 times 7 times 6 times 5 factorial over 5 factorial times 3 factorial. I think you can see why I wrote that out, so I could cancel the 5 factorials. And then also, remember where this happened one other time, 3 times 2 times 1 is 6. So I can cancel 3 factorial with 6, so that leaves 56. So this is equal to 56. Okay, so the probability then of choosing 3 points, it says what is the probability that they all lay on the same side of the rectangle? Well, you'll notice that unlike the last examples, there's more than one way that can happen. I could choose these 3 that are A, B, and C that are on the same side, or I could choose these 3, C, D, E, that are on the same side, or G, F, E that are on the same side, or A, H, G that are on the same side. So you can see that there are 4 different ways of choosing points that lie all on the same side. 4 different ways out of 46. So the probability then is going to be 4 out of 56, and that reduces to 1 out of 14. Okay, at this point, I imagine you feel like your head is swimming. There was a lot of stuff in this lesson. But fear not, when we're in class together, we're going to do a whole bunch of examples, and I think by the end of the next class period, you're going to feel a whole lot more confident about this material. I just wanted to get the notes out of the way so that we can spend our class time practicing problems and helping you understand the material better. So I will see you in class, and if you have any questions, you can ask me then.